Chapter 6, Lesson 1 of Geometry, and in this lesson, or in this video rather, I want to do a number of examples where we classify quadrilaterals based upon a calculation that we do of their slope and then their distance, or the lengths of their sides using the distance formula. So as a quick review before we jump into a number of examples is, in order to classify a quadrilateral, you remember the first question we asked were, how many pairs of parallel sides are there? Well, how can we calculate that or determine that using algebra? Well, what we'll want to do is we're going to use the slope formula, and we'll have to determine the slope of all the sides. And from earlier, you remember that the parallel sides will have the same slope. So when I calculate them up here in step 1, I'll then look at the opposite ones and see if they're the same. If they're the same, they're parallel, and in doing so, then we'll be able to identify which sides are parallel or how many pairs of parallel sides that we have. You remember then when we looked at if we had a parallelogram, we asked the question, how many right angles are there when we're trying to identify a rectangle? Well, how can we use, again, algebra to help us determine rectangles or right angles? Right angles are determined by perpendicular lines. So if we knew the slopes, we'd be looking for perpendicular slopes. And we talked about using the negative reciprocal, or that perpendicular lines would have slopes that are negative reciprocals of each other. So again, we would use the slope formula to determine all the slopes, and then we look at the ones that are next to each other and see if they are perpendicular, because if they're perpendicular, then we have a right angle. Okay. The other question that we looked at when identifying a rhombus are all the sides the same length? So if we need to determine the length of a segment, you remember we use the distance formula. So we'll use the distance formula in order to determine if the lengths are all the same side. Now, as a little hint here, as we're using the distance formula and we have to take that square root, you don't need to calculate what the decimal approximation of those are. Just leave the square roots. All you need to know is, are they the same? In other words, the square root of 13, is that the same length as the square root of 13? Well, yes. You don't need to know what the decimal approximation is. They're both the same, so they will be equal. So by calculating the slope and using the distance formula, we should be able to identify or classify these quadrilaterals. So let's take our first example here. Now again, I'll do 3 or 4 of these, and then you watch as many as you need, but I think you can probably pick this up pretty quickly. All right, so we want to determine the most precise name for the quadrilateral that has these coordinates. So the first thing you'll want to do is to graph these coordinates on a little piece of graph paper and draw the figure. Now, we can probably guess what's parallel and what's not, but again, from our learning earlier in the year, we know that we can't make any assumptions. We have to know by either tick marks, or we have to have a way to conclude it. And the way we're going to conclude it in these exercises is to do it algebraically. So what we're going to have to do is determine the slope for all 4 sides, and then we'll compare the slopes. So if I'm looking at this point here and this point here, in order to determine the slope of AD, I need to take the 2 y coordinates. So I take 5 minus 1, and then I subtract the 2 x coordinates, 3 minus 2. Now the only thing here is make sure you have to keep the same ones in order. So if I use the 5 first, then I have to use the x coordinate that goes with it first. So 5 minus 1 is 4, and 3 minus 2 is 1, which reduces to 4. So that's the slope of AD. Now I have to do the slope of, let's go ahead and do the opposite side, since that's what we're interested in. So now we'll do the slope of BC. So in BC, I take the 2 y coordinates, so I do 6 minus 2 over 7 minus 6, and so that's 4 over 1, which is 4. So those slopes are identical. So that means that those 2 sides are parallel. So I have 1 pair of sides that are parallel so far. Now I have to do the other pair of parallel sides and see if those are parallel. So I'm going to do the segment AB here. So again, I'm going to do the slope formula. So I take the y minus the y. So I'm going to go 6 minus 5. And then I use 7 minus 3. 7 minus 3. So 6 minus 5 is 1 over 4. So that's 1 over 4. Okay? And then I do the slope of DC. So we'll do DC because that's the opposite side. So I'll take this y minus this y. So that's 2 minus 1. And then this y minus this y, 6 minus 2, and do the math. So this is 1 over 4. So I notice that these two are identical, so therefore these sides are parallel. So I have two pairs of parallel sides, which means I have a parallelogram. Okay? Now, is that the most precise thing? Well, you remember when we have a parallelogram, once we know that, we have two other questions we have to ask. Are the right angles? And if it is, it's a rectangle, which is more precise. And then we have to see, are the sides equal? Because if the answer is yes, then that's a rhombus, and that's more precise. Okay? Now, we can answer the question about right angles by looking at the slopes. And if we looked at the slopes, or if we think about a rectangle, this has to be a right angle. And for this to be a right angle, DA, or AD, has to be perpendicular to AB, which means those slopes need to be opposite sines and reciprocals of each other. So if I go back to the slope for AD, which is 4, which is this line, and I look at the slope of AB, which is this line, 1/4, are they opposite sines and reciprocals? Well, they are reciprocals of each other because this is 4 and this is 1/4. However, they are not opposite sines. Therefore, this cannot be a rectangle because this is not a right angle. So that takes care of rectangle. But now we have to look, well, maybe it's a rhombus. Maybe all the sides are the same length. So in order to do that, I have to use the distance formula in order to figure out the lengths. So now I'm going to have to do the distance formula. Okay, so we have to do the length of each side. So the distance formula, I'll write it here, and you're going to have to just kind of remember this, and it's on the room, or it's on the wall in the room. You take the two x coordinates, subtract them and square it, and then you take the two y coordinates, subtract it and square it. Okay, so let's do AB first. We'll do AB first. So what's the length of AB? Okay, so I'm going to take two x coordinates, so 7 minus 3, and square it. 7 minus 3 squared, and then I'm going to add the two y coordinates, 6 minus 5, and I'm going to square that. Okay, so 7 minus 3 is 4, and 4 squared is 16. So that's the square root of 16. And then 6 minus 5 is 1. So that's 1, and 1 squared is 1. So this length of this is the square root of 17. Now, I don't need to calculate any more than that. I know that the length of this now is the square root of 17. So now I'll do the next side and see what the length of that is. So we'll do BC, and we're going to repeat this for all four sides. Now, I only have to keep going as long as I keep getting the same answer. Because you remember with a rhombus, all four sides are the same length. So if one of them ends up being different, then I can stop because I know it's not a rhombus. Okay? All right, so we'll do BC here. So I take the two x coordinates, which is 7 and 6. I'm going to subtract those, 7 minus 6, and I'm going to square it. And then the two y coordinates are 6 and 2. So 6 minus 2, square it. So 7 minus 6 is 1, and 1 squared is 1. 6 minus 2 is 4. 4 squared is 16, so it's going to be the square root of 17. So this one is also the square root of 17, so we're the same. So now I'll do DC. And I know what you're thinking right now. Can't we just say it is because it looks like it is, and you know what my answer is, right? No, you can't, because you can't make assumptions by just what things appear to be. You must do the arithmetic and prove it. Okay, so these are the two x coordinates for DC and the two y. So 6 minus 4 is 2. No, 6 minus 2, excuse me, is 4. 4 squared is 16. That's 1 squared, so square root of 17. We're good. And now I do AD. So yes, you have to do all this work on every single problem to make sure you can for certain say that you have proved that it is the name that you're going to use. Okay, so finally we got 3 minus 2 here, squared, plus, and then we have 5 minus 1. So that's 1's squared is 1. This is 4 squared 16. So this is the square root of 17. So you can see that the most precise name then is not a parallelogram, but because all four sides are congruent, this figure's most precise name is a rhombus. Okay? So again, I'm going to do 3 or 4, maybe even 5 more examples. You watch as many as you think you need to help you do these. Probably, you know, another couple and you should have it. It really just comes down to remembering slope formula and being able to do the arithmetic, and then the distance formula and being able to do the arithmetic, and then making those decisions based upon those values that you get. All right? For our next example then, we're going to graph these, and we put them in a coordinate plane, and this is what we get. Now, we know that it looks like a trapezoid, which means, if you remember, one pair of sides are parallel. So that would be this side here and this side here. So those would be the one pair of parallel sides. Then we had the more precise name, the isosceles trapezoid, and you remember with the isosceles trapezoid, these opposite sides that aren't parallel are equal in length. So I'm going to need to use the distance formula to determine that, and I'm going to need the slope formula only for these two to figure out if these are parallel. So we'll go ahead and do that. So we'll do the slope formula first. So the slope formula, you remember, I don't need that. We'll do the slope formula for EH. So I take the y coordinates, which are 1 and 1, 1 minus 1, and I'll subtract the x coordinates, 2 minus, and then I have a negative 3, and a minus a negative 3 ends up being positive 3. Now 1 minus 1 is 0, and anything over 0, 0 over anything, excuse me, is 0. So the slope of that line is 0. And then we'll do FG. And again, we'll take the y coordinates, which are negative 3 minus, and then the other one, negative 3, and a negative minus a negative is a positive. And you'll notice that I'm going to get 0 here. I see that that minus that is 0, so it doesn't even matter what's down here. It could be anything. It doesn't even matter, and it's going to be 0. So in looking at that, the slopes are the same, so I do know for certain then that we do have a trapezoid. Now, to prove that these are not parallel, I would have to figure out the slope of these, and I should get different slopes. So we'll have to figure out the slope of EF and FHG. Now, I'm going to cut you some slack here and say that those are obviously not parallel, so we're not even going to do the arithmetic to do that. Okay, so we're going to make that assumption. That's pretty safe to say. So then the only thing we need to figure out now is it isosceles trapezoid, and that would mean the lengths of these two are equal, so we're going to have to use the distance formula for both of those. So we'll do the distance formula for EF first. So that's the square root of the 2x coordinates, so that's negative 3, and then it's minus, and then I have negative 7, so minus and negative 7 is plus 7 squared plus, and then I have 1 minus, and then I have a negative 3, so minus and negative again is positive squared. So 7 and negative 3 is 4, 4 squared is 16, plus 3 plus 1 is 4, that's another 16, so that's the square root of 32. So the length of this is the square root of 32. So now I'll need to do the other one, HG. And again, we should, if it is congruent, get the same thing. So here I have the x's of 2 and 6, so I'm going to do 6 minus 2 squared plus, and then the y's of 1 and negative 3. So 1 minus, and again, negative 3 is a plus. So that's going to be 4 squared, which is 16, plus 4 squared, which is 16. So that ends up being the same thing. So the length of this one is also the square root of 32. So I can give this the even more precise name of an isosceles trapezoid, because I showed that the opposite sides are parallel, one pair, and then the non-parallel sides are congruent. Actually, I don't have any more examples of this type, so we'll wrap it up there. If you need more help, then simply rewind the video and go ahead and watch these again. To summarize what we worked on in this lesson, we can use slope and distance formula to help us classify these quadrilaterals, because slope can help us determine whether sides are parallel or whether they're perpendicular, forming right angles, which helps us classify parallelograms. And then the distance formula can help us determine the lengths of sides, which help us when we need to identify an isosceles trapezoid or even a rhombus, or if we're looking at kites where we need to have the adjacent sides equal in length. So those you just need to remember, and that kind of summarizes everything you need to know. And I hope that was helpful, and we will see you in class.